Hey, how's it going, everyone? This is FixerMed. Welcome to my high yield biochemistry review series for the USMLE Step 1, NBME CBSE, and NBME CAS examinations. This will be part 14 of my multi part video series detailing and describing the entire discipline of biochemistry in a high yield but comprehensive manner. So, without further ado, let's go ahead and get started on today's content. So I wanted to go ahead and give some background information on galactose metabolism and fructose metabolism on the next slide. So let's go ahead and break this down. Galactose metabolism mainly involves the conversion of galactose to glucose 1-phosphate through a series of enzymatic steps. The first key enzyme in this pathway is galactokinase, which phosphorylates galactose to form galactose 1-phosphate. Subsequently, galactose 1-phosphate uridyl transferase catalyzes the conversion of galactose 1-phosphate to UDP galactose. The final step is mediated by UDP galactose 4 epimerase, which transforms UDP galactose into UDP glucose. Now, UDP stands for uridine diphosphate, but I just don't want to say it over and over again, but so that's why I say UDP. Ultimately, the UDP glycose can be further metabolized to glucose 1-phosphate and incorporated into glycolysis for energy production. Let's go ahead and cover fructose metabolism. Fructose metabolism involves the conversion of fructose to fructose 1-phosphate in the liver. The key enzyme in this process is fructokinase, which phosphorylates fructose to form fructose 1-phosphate. Aldolase B then cleaves fructose 1-phosphate into dihydroxyacetone phosphate, DHAP, and glyceraldehyde. These products enter glycolysis, contributing to energy production. Importantly, deficiencies in aldolase B can lead to hereditary fructose intolerance, a condition characterized by the accumulation of fructose 1-phosphate and subsequent liver dysfunction. Now, I will say, try and memorize these pathways if you can. I'd say they're mid-yield, but if you can know the pathways, you should be set for a lot of problems. If you can just draw those pathways out from memory, you should be good to go. Like, you can identify where the error is occurring, understand what product isn't being metabolized, etc., etc. So, let's get to the main topic of today's lesson, sugar disorders. We're going to open up with galactokinase deficiency. The main enzyme deficiency in here is with galactokinase. From birth, individuals with this condition exhibit an inability to metabolize milk lactose, leading to the conversion of galactose to galactitol and glucose. Early screening through a heel prick test allows for a timely detection. Notably, neonates with this condition may present with cataracts, a distinctive clinical feature. The pathophysiological mechanism involves aldose reductase, which converts galactose to galactitol, creating an osmotic pull within the lens. Importantly, this form of galactosemia is milder in its clinical manifestation compared to classic galactosemia. Let's move on to the next one. We have classic galactosemia. The main enzyme deficiency observed here is with galactose 1-phosphate uridyl transferase. From birth, individuals with this metabolic disorder exhibit impaired conversion of milk lactose to galactose and glucose, leading to consequential clinical manifestations. Early detection is facilitated through a heel prick test. Neonates may present with cataracts, and as the condition progresses, additional symptoms such as hepatomegaly, jaundice, and hypoglycemia become apparent. Notably, this disorder is associated with an increased susceptibility to E. coli sepsis. The underlying mechanism involves the trapping of glucose 1-phosphate in the liver, resulting in phosphate sequestration. Importantly, the severity of this condition surpasses that of glucokinase deficiency. Just keep that in mind. Sorry, not glucokinase, galactokinase deficiency. Moving on, we have essential fructosuria. The main enzyme deficiency observed in essential fructosuria is with fructokinase. This benign condition is characterized by the mere presence of reducing sugars in the urine, a key diagnostic marker. Notably, the urine test for glucose oxidase is negative, providing a crucial distinction from other conditions where glucose is typically detected. The negative result in the glucose oxidase test indicates that the observed reducing sugars in the urine are not glucose. This high yield information highlights the importance of recognizing this benign state when assessing urinary constituents. Let's move on to the next condition. We have hereditary fructose intolerance. The main enzyme deficiency observed here is with aldolase B. Upon the introduction of dietary sources such as juice, fruit, honey, and table sugar, individuals with this metabolic disorder manifest hepatomegaly, jaundice, and hypoglycemia. A pivotal mechanism involves the trapping of fructose 1-phosphate in the liver, leading to the sequestration of phosphate. This condition, marked by its clinical triad and underlying pathophysiology, highlights the significance of recognizing the dietary triggers and associated symptoms. The concise presentation emphasizes the key aspects of this metabolic disorder for a comprehensive understanding. So, some important information. Sugar disorders, encompassing both galactose and fructose disorders, share the common feature of presenting with reducing sugars in the urine, a crucial diagnostic descriptor. Galactose disorders are typically identified through a heel prick test shortly after birth, allowing for early detection. The distinct timelines of manifestation between these disorders are noteworthy, with galactose disorders surfacing earlier due to the ingestion of milk, which comprises lactose, a compound of galactose and glucose. In contrast, fructose disorders become evident only when the infant begins consuming fruits, juice, honey, and table sugar, as these contain sucrose, composed of fructose and glucose. This concise presentation emphasizes the key diagnostic markers and timelines for identification of sugar disorders. So with that, let's go ahead and get started on some questions. NBME application-based reasoning question. A 4-day-old newborn exhibits vomiting, irritability, and refusal to feed after being introduced to formula. A urine test shows the presence of reducing sugars. A heel prick test reveals a positive result. Which of the following enzymes is most likely deficient in this patient? Pretty straightforward question. If you guys need more time, please feel free to pause the video. Otherwise, moving on now. The symptoms in positive heel prick test are indicative of galactosemia. Galactose 1-phosphate uridyl transferase deficiency leads to the accumulation of galactose 1-phosphate, causing the observed clinical manifestations. Therefore, the correct answer here is C, galactose 1-phosphate uridyl transferase. Let's see why the other answer choices are incorrect. In glucose 6-phosphatase, the deficiency in glucose 6-phosphatase is associated with glycogen storage diseases and would not manifest with symptoms of galactosemia. Galactokinase deficiency results in a less severe form of galactosemia and typically presents with cataracts, not the described symptoms. Aldolase B, Aldolase B is involved in fructose metabolism, and its deficiency leads to hereditary fructose intolerance, not galactosemia. Fructokinase is part of fructose metabolism and is not related to the symptoms described in galactosemia. Let's move on to the next question. Next question, we have a 6-month-old infant that develops vomiting, hepatomegaly, and jaundice shortly after introducing fruit juices into the diet. Laboratory tests reveal reducing sugars in the urine. Which enzyme deficiency is most likely responsible for these symptoms? All right, I think I gave you enough time here. If you need more time, please feel free to pause the video. Otherwise, moving on now. The symptoms described along with the introduction of fruit juices are indicative of hereditary fructose intolerance. Aldolase B deficiency results in the accumulation of fructose 1-phosphate, causing hepatic dysfunction and the observed clinical features. Therefore, the correct answer is A, aldolase B. Let's see why the other answer choices are incorrect. The other incorrect answer choices can be explained as follows. Galactokinase deficiency leads to a milder form of galactosemia and typically presents with cataracts, not the symptoms described here. Fructokinase is not associated with the symptoms of hereditary fructose intolerance described in this case. Galactose 1-phosphate uridyl transferase. This enzyme is related to galactose metabolism, and its deficiency leads to galactosemia, not hereditary fructose intolerance. Glucose 6-phosphatase. Glucose 6-phosphatase deficiency is associated with glycogen storage diseases and would not result in the symptoms of hereditary fructose intolerance. Now, that's all we have for sugar disorders, guys. If you have any questions, comments, or concerns, please feel free to leave them in the comment section below. If not, this is FixerMed signing off. Good luck studying, guys. If you guys need anything related to what we just covered or anything pertinent to USMLE and NBME, also let me know in the comment section below. If not, I'll be signing off now. So goodbye.